This is a walkthrough of problem 2 on practice exam 1 of module 11 in the book Problem Solving Guide for Mechanics and Thermodynamics. We have a 20 centimeter by 10 centimeter piece of metal foil at a temperature of 20 degrees Celsius. It's placed in an oven at 200 degrees Celsius and as a result gains 0.6 square centimeters of area. What is the linear thermal expansion coefficient of the metal? Well, let's draw a piece of metal. Maybe we'll get partial credit for that. Its area is 20 times 10 square centimeters, 200 square centimeters. So far, so good. When it's heated from 20 to 200, its area becomes 200.6 square centimeters because it gains 0.6 square centimeters of area. What do we do now? We got any moves? We got to think. We got to think hard. How about calculus? Let's use calculus. We can derive the product rule along the way. As a bonus, we're going to derive the product rule. The area of a rectangle is base times height. So let's put those on the diagram. B for base, H for height. We're on our way. Differential calculus is aptly named because it's all about differences. We want to know the response of the area when we change both the height and the base. When we change B by dB, and we change H by dH, what is dA? How much does the area change? It's easy to calculate. We just need some algebra. The original area is, who's got it? It's B times H, area of a rectangle. The different area is different by dA. And we have a different rectangle. Its area is A plus dA. Its base is B plus dB, and its height is H plus dH. It's a different rectangle. It's got a different area, it's got a different base, it's got a different height. We can FOIL this out to give base times height. That's the first. Lasts are dB and dH, and then the cross terms are BDH and HDB. This is the original area of the rectangle, and so is B times H. So we can get rid of those. We can cancel the original area, and we get dA is BDH plus HDB plus dBdH. And these are infinitesimals, so we can throw out the dBdH term. And we're 100% correct to do so. We just throw it out. This equation is true. It's exact, it's not approximate, even though we threw that out, because that's 0. Compared to this, it's hard to understand because that's what makes calculus hard to understand. dA, dH, and dB are not numbers. If they were numbers, you'd get the wrong answer because you're throwing out that term. But they're not numbers. They're ideas. They're infinitesimals. This is the product rule, and it's exact. dA is BDH plus HDB. A is B times H. When you take the derivative of that, you say, okay, first times the derivative of the second plus the second times the derivative of the first, which is the product rule. We can see where this comes from. And this is so important if you want to understand what's going on rather than remembering rules. So here's the original rectangle. I'm going to make it a little bit bigger. I'm going to make the height bigger and the base bigger. Boom. Now I'm going to draw the original rectangle again. The height changed by dH. That's the change in height. The new height is H plus dH. The base changed by dB. B plus dB is the new base. And here's the new area. These three pieces right here. This piece, this long rectangle on top, has a base B and a height dH. That is BDH. This area has a height H, this long thin rectangle, height H with dB. Its area is HDB. That's this term. We threw away this one, dB and dH, dB times dH. And if it's infinitesimal, we can throw that out. If it's not infinitesimal, we're not supposed to throw it out. If we're writing dBs and dHs instead of delta H's and delta B's, then we can throw it out. So let's use the equation we just derived to answer the question. dA is BDH plus HDB. The change in area, dA, is 0.6 square centimeters, B is 20, H is 10, and we know that dB is 2dH because B is twice as big as H. So I'm going to plug in numbers for differentials. You're not supposed to do that. But I know I know I threw out dBdH, so I know I'm not going to get the exact answer because I threw out dBdH. But we'll see how big dBdH is. So I have a dH here, and I can solve for dH. It's 0.015 centimeters, which is small. So h starts out at 10, and it goes up to 10.015. The base starts off at 20. It goes over to 20.03. So now we can calculate the linear expansion coefficient. Delta L is alpha L delta T. There's delta L, and there's alpha L delta T. This is the height, the change for the height. There's the temperature change, and I get 8.33 times 10 to the minus 6 per degree Celsius. And that's the answer. Without calculus, you can say, all right, I'm just going to divide this into two squares. Two 10 by 10 squares. So the change in each, since the total change is 0.6, the change in each is going to be 0.3. So there it is. So now I have 10 by 10, which is 100, and now my new area is 100.3. I just got to take the square root of that. What's the square root of 100.3? It's 10.01499. So we're using calculus and throwing away the dBdH, we got 10.015. The exact answer is 10.01499. That's close enough for me. That's problem 2.